wire 4 times, you make quadruple the current. See, each of these is really subtle. And 4 of them in 4 separate wires is almost imperceptible. But when you quadruple that in a single wire, that's starting to add up. And now you can imagine if we had a bazillion coils in a wire with 6 or 8 or 10 magnets. Notice it took all these coils of wire just to light this super tiny light bulb. But if we can bunch up a whole lot of magnets and a whole lot of wires, all we gotta do is figure out how to spin the magnets. And we can make electricity. Almost every single power plant on Earth is just another engineering trick to spin the magnet past the wires. So like, you could hold this up in the air and put some blades on it and let the wind do it, or you could put paddles and let water shoot across those paddles, or you could tie it up to the chain on a bicycle and make somebody ride a stationary bicycle, or you could put a big hamster wheel and have the hamsters running. All you gotta do is figure out how to spin those magnets. By the way, a nuclear power plant is just this really dangerous way to boil water so you can use steam to spin a turbine. Like, this part is the same. Every power plant on Earth uses the same engineers. It's basically the same technology, the same metals, probably the same factories to do this thing. Now, there's a lot of details about how to adapt a turbine. So someday, if you want to be a PhD in whatever kind of engineering this is, you can sort out what all those different doohickeys and whatchamacallums do. And there's all sorts of fascinating development in making turbines more efficient or bigger. But when you talk to the College Board, all you got to say is turbine and generator. That's a turbine, and that thing right next to it is a generator. You use a turbine to spin a generator. That's it. And look, that's a turbine generator, that's a turbine generator. Here's a turbine generator, that's a turbine generator. It's right here, it's right there, it's right here, it's right there. There's another one, here's another one. There will be one here on Friday. There will be one here on Tuesday. Because everything else we got to say about making electricity is turbines. The only generation without a turbine is this. We'll come back to that. Yeah, bro.
What about hydrogen fuel cell?
That's not technically a generation of electricity.
That's your story. Okay.
It's better to think of hydrogen fuel cells as a chargeable battery. Anybody want to ask me about that, or can I move on? Okay, next. I'd like you to imagine, for the sake of conversation, just for a moment, I'll throw it at you. I'd like you to imagine that this is metal. We'll say it's a bar of steel. And this is really, really, really hot liquid. If I take my boiling hot water and I put my metal bar in there for like 10 minutes, then I take it out, what's happened to the temperature of my metal bar? Hey! And what happened to the temperature of my boiling water? It went down. Good job. Heat exchange. Why did I make it metal?
Because of conductivity.
Hey, good job. This is all obvious, right? What if I have cold water in a hot ass bar and I go like that? What's going to happen to the temperature of the water? Hey, good job. Now what if this was a pipe? And I had fancy plumbing so that it went through my water. You can pretend that this goes through my water. And in this pipe, I run an incoming hot fluid. So I'm pushing hot fluid through a metal pipe that's in contact with colder water. What's going to happen to the temperature of the water in the cup?
Rise.
It will rise. And then as this water leaves, its temperature will have gone down,
Yes.
right? Because it's passed its heat to whatever was in the cup. Are we all cool? It's called a heat exchanger. I'm going to put these all over the map too. See? Hot goes in, cold comes out, but it made steam. Yeah? Heat exchange? You can go backward. Pushing cold, it comes out hot. It's a coolant. So, look over there. We are cooling the ocean by taking some heat out of it. Good? When we do nuclear power plants, there's going to be like 3 of those in the same system. Anybody want to ask me anything about heat exchangers? Yeah?
In 29, the old version and the new version, are they basically just the same except one of them?
Don't get ahead of me. Heat exchanger, key word that you'll want to use. Heat transfer, heat exchange, cooling, heating, coolant, heat source. You probably understand all this because it's plain English, so I think you'll be okay. Back to that day that you all made the wave going across the classroom. Liam, if those grids are a little sloppy, it's no problem.
Oh, okay. Well,
Back to the day that you guys did the wave going across the classroom. I just want to remind you that in real physics, electrical current is the transfer of electron excitement among neighboring atoms. Electron excitement, transfer neighboring atoms. But the shortcut that we use is we say electrons are flowing. And that's bogus, but that's the easiest way to think about all this. Are we okay with that? Electrons don't actually go anywhere. It's not like you run out of electrons at the electrical power plant. Your house doesn't get full of electrons when you use electricity. Okay. I think we might be ready to do this thing. There was something else I wanted to remind you. I'll probably remember in a minute. Yeah, I think we're good to go. Okay. You ready to do this? You've had a lot of time to catch up on drawings, but I want to remind you that you should not be drawing something different than what you're trying to learn, because your brain doesn't do 2 separate channels through 2 separate systems very well. You can do 2 channels on the same topic, but not 2 channels, 2 topics. Please look up. This is an old school solar panel. Today there have been a lot of changes in the technology, but the concept is still the same. There are modern solar panels which use different ingredients, but the basics are good. We have silicon with boron, a semi-permeable electrolyte layer, and silicon. And that's okay, I'm going to go over what these mean.
Can you say the second one?
Yeah, I'm going to do all that, don't worry about it. Don't get ahead of me. Watch. First, silicon. Silicon is not silicone. Silicone is like a squishy, flexible, sort of rubbery stuff that you put on your window seals or around the bathtub or like in an aquarium or in fake boobs. But that's silicone, and that's different from silicon. When you write them, that E makes a huge difference. silicone, silicon,
So that's spelled with an E?
that's spelled without, because it's the element, silicon. No E. Oh, hey.
Jokes, dude. He fucking texted me for that.
Can you imagine how much time and material was wasted by Colin Wells? Okay, lucky for me, I remember where things go. Silicon, for anybody who speaks physics, silicon is a really good material to use to transmit electricity because it has 1, 2, 3, 4 valence electrons in the third ring. That means that when you build a grid out of silicon, electricity transmits perfectly. Silicon is a very good conductor. That's why we make microchips out of silicon. That's why it's called Silicon Valley, because engineering electronics. Are you okay with all this, silicon? It's really important because it's a clean conductor. You probably want to know that.
I mean, it's fine.
Both the top and the bottom have silicon so that electricity can move cleanly. Any excitement can be transferred perfectly. The top layer has boron. And nowadays, I'll warn you that modern solar panels use other elements. But back in the 70s, this was the most basic one. It's the easiest one to explain. Oh, hey, how nice. Boron's already clear. Anybody need Post-its? Boron. For anybody who remembers chemistry, has 1s2, 2s2, 2p1 electrons. Remember chemistry? 2p1 means, this is the part you would need in your notes, boron has one loosely held electron. One electron that's very excitable. Boron is really easy to make it lose an electron, so to speak. It takes just a little nudge to excite boron. Just a little nudge, because it has a 2p1. And in the middle, we have that thing that you were all asking about. You can call it a semi-permeable electrolyte layer or a semi-permeable electrolyte membrane. And we can break down these words and I'll help you get ready for notes. Semi-permeable means stuff can go through sometimes. Electrolyte means charged particles. And membrane is a thin layer. So, you can make a semi-permeable electrolyte membrane that keeps out all positive charges, or you can make one that keeps out all negative charges, or you can make one that only lets positive charges go to the right, or this kind where only negative charges can go down the panel. See those little gates I drew? Those are for negative charges only. Look, negative, down the panel. When sunlight hits the boron goes, whoa, and the electron gets excited. Anybody know the charge of an electron?
Negative.
So which way is it going to go in a solar panel? Because that's just how you built the solar panel. but that particular membrane only lets negative charges go down. So when the boron gets excited, the electron will migrate to the bottom. And this one too. And this one also. And this one too. And also this one. When you take away electrons from an atom, what happens to the charge of that atom?
Positive.
Becomes positive, that's right. So now we've got boron that's a little too positive on the top side. In other words, we have a bunch of positive charges on this side of the panel and a bunch of negative charges on this side of the panel. I'll repeat all of this, but you should be taking notes because you'll have to explain it to the College Board. What we've done is a really important physics term. We have created polarity. One side of the panel is net positive, one side of the panel is net negative. All the electrons have shifted to the bottom. Or there's more electron excitement at the bottom, if we want to be specific.
Got more tape?
Look inside my SAT supplies box.
Okay.
Children, what's a household item with a plus on one end and a negative on the other end? Hey! So now, if I put a wire between those two, current is going to flow. You know, because opposites attract. So like, all those electrons want to go home to daddy or whatever. And as they travel through the wire, they do work. A solar panel is just an interesting way to have a battery that's polarized by sunlight, kind of. Sunlight hits the top of the membrane and all those electrons travel to the bottom, so they want to work. And when they come back, the boron can't hold them. It's too excited because it's in the sunlight. So you can just keep doing this. You're so glad you're in second period. Because in second period, we have sunlight in the room. And I happen to own
some more tape for you.
this really cool car.
Fluid, dude.
I gotta stand here so that I can block the sunlight with my own body's shadow.
Are you sure?
And then when I get out of the way, hey-o! Nobody's blown away by that magic? I hit all of you. No, I'll talk to you yet. Watch. As long as this thing is in the sunlight, those wheels are going to spin. And literally, like, until the sun goes down, when those electrons come back to the top layer, the boron can't hold them because it's got that really excitable 2p1 electron. The sunlight keeps hitting it and it just keeps like, getting too excited and losing it. It keeps migrating to the bottom, keeps running through the wire. I color-coded this in the way that every physics teacher will ever color-code this in all the history of your classes, because there's this like international language of electricians where the side that's more negative gets a red wire. So you can see it someday. If you want to just walk up, I'll leave this thing on my cart. It's got like metal wires on the top that are all soldered to a black wire, and then metal wires on the bottom that are obviously visibly soldered to a red wire. Red for where the electrons are, red for energy state, red for heat. So there it is, that red is a red wire doing all this work, and then the black comes back. Yeah, bro.
So if they're using the same electrons the whole time,
Yeah.
but technically energy gets less and less efficient, does it get less efficient?
There must be an efficiency drop in this system somewhere, but basically at the atomic level, I think this is pretty close to eternal. Like in outer space, solar panels, I don't think they wear out unless they're physically damaged. So like satellites with solar panels, they keep going. There you have it. Here comes your one-time quick repetition. Silicon with boron, because boron has a loosely held electron. Semi-permeable electrolyte membrane lets negative charges go down the panel only. That's just the one that we chose to build for this item. You can make SPEMs that go positive right. But this one is negative down. That doesn't even look like it's down the panel. Let me try to make that more clearly down the panel. That way. That's your SPEM. On the bottom, you just have silicon. It just transmits electricity perfectly. That's why silicon, that's why microchips. Sunlight, boron loses hold on an electron. It migrates down the panel. You've created polarity. Positive charge, negative charge, work, current. Hey. Only problem is, you don't always have sunlight. Two ways to solve that. The old school way that the hippies used to do when they lived off the grid is called off-grid systems. This system sucks because batteries are expensive, inefficient, they require maintenance. Batteries are really inefficient. It takes this much charge to put this much power into a battery, and then when you use that battery, you're only going to get this much charge out of it. Batteries are dumb. Like the best batteries in the world, like 30% efficiency maybe, if they're like in a vacuum that's refrigerated, managed by robots. Like, I think the theoretical maximum for batteries, total input to output, is like 40%. And that's like theoretical maximum. So batteries are dumb because it's just batteries suck. It's just the batteries are the weakness. The concept is good. If we could store it another way, fine. But batteries no good. So solution number B is the one that they do everywhere in your neighborhoods. Every time that you see solar panels on a house, unless you're like on a weird sailboat in the middle of the ocean or surrounded by weirdos and Bigfoot in the forest somewhere, every set of solar panels that you'll ever see in your day-to-day Santa Barbara life is B. That's called on-grid or grid-connected. These systems are really smart. They're really efficient. They're less expensive. As a matter of fact, if you do it right, you can even make a little bit of money doing this. And the way that system B works is your extra bonus electricity, instead of putting it in a battery, you just sell it back to the electrical company. You push electricity onto the grid so that you can run your neighbor's fridge and your other neighbor's fridge and the other neighbor's fridge. So all day long, they're buying electricity from you. You're a power plant. And then at night, you use that credit to buy electricity from a coal-burning power plant out on the grid somewhere. So the meter spins in your favor during the day, and then you buy back electricity at night. Two-way meter, that's why there's arrows going left and arrows going right. And by the way, that's surprisingly the biggest weakness, is that many parts of the United States and the rest of the world, they just don't have that kind of meter. Like that little box is the problem. Because technically the physics of measuring electricity both directions is more expensive, so those meters are not always available. Yeah.
What does the second bullet point say under grid connect?
It says this system rules.
When it said rules, I didn't know if it was like there's
No.
certain rules you have to follow.
No, I don't follow no rules. Yeah.
So theoretically, to make money, you could like sell off the energy and then at night use candles instead of like.
Yeah. Yeah, theoretically, yes.
And it's like more efficient during the summer because there's more daylight hours.
Correct.
You can profit during the summer.
What about when it's raining?
Then you don't make
So
electricity.
most people who have solar panels, by like September, October, they have like a couple $100 electricity credit. They owe negative dollars, like technically Edison owes you. And then as you head into the fall and winter, the days get shorter, you get more cloudy days. So you have more days where you buy than days that you sell. And so you start to eat up your credit. And you could build a bigger solar field on a bigger house with more roof space and just do more sales than purchases, and then technically they'll cut you a check. It's just not really worth it because they don't pay you the same as you pay them. They buy it from you at wholesale, you buy it from them at retail. So the sweet spot is to just make the exact amount that you purchase per year. Okay. If we're done with solar panels, everything else, we're just going to figure out how to spin a turbine. Are we done with solar panels? Okay then. I'm moving on. Next, we'll talk about solar thermal electricity, which is also known as concentrated solar power. Concentrated. Like a magnifying glass that you use to burn ants or harm other animals.
No childhood.
So you light your own farts on fire and you kill ants. By
So
lighting
does
them on
David and Sadie
Yeah,
and
I
Casey.
fire. Oh, why?
I was friends with Colin, you know,
That's a mistake.
I mostly something killed fire.
Same idea as using a magnifying glass. You're taking a whole bunch of light and then you focus it to light a fire. People etch wood with it. You can like make cool patterns in leather with this. Or you can just reflect a bunch of sunlight onto a pipe that's full of liquid and that makes really hot liquid. So if you got enough pipes and enough mirrors, you can make really hot liquid.
Or is that just solar
Oh, I'll get to that one next. Similar. I got you, man. The only place where you're likely to see one of these is when you land at Kona in Hawaii. No, like every person that's ever flown to the Big Island, at the very, very end of your flight, you make the final approach to the landing strip, and you fly over the airport, over the cliff, over the ocean, and then you come onto the landing strip back on land. That flight path is like required for all planes when they land on the Big Island. And when you're doing this, down the right wingtip, there's one of these. No joke, I tried to photograph it when I was going to the Big Island, and then I dropped my phone and it broke my screen. I'll never forget.
Cover your phone. Is it on the plane?
Yeah, in the plane. Yeah,
Dropped it
yeah.
out of the window.
Right, yes. I had rolled down the window. Once you have hot stuff, you can make some steam and spin a turbine. And does everybody realize that steam is pressurized? Like a lot of steam with a small aperture? Everybody get that?
Yeah.
Like, you know those tea kettles that whistle?
Yeah.
and you've got a whole bunch of surface area making steam, but you let it out through a small port, so it makes a lot of noise. You can like pull off the whistle, it doesn't make any noise, right? It's just like, so it's not like an open container. That would just be like, that's actually focused through a small aperture under pressure. Does that make sense to everybody? Now, this is old school. And the dollars of running one of these with all the little robots that have to track the sunlight and all the plumbing and all the pipe and the amount of coolant, the amount of boiling, it's just not good enough. So after people built that one in Hawaii, actually, a bunch of nerds got together and they're like, well, what if an area has less sunlight? What if an area has more people? They were like, we need another way to focus sunlight. And then people started to design other systems to try to figure out how to focus more sunlight. And then somebody had this idea, and everything changed. I think it was an Israeli dude.
Yes.
Boo! This turned out to be like a really good idea. Because if you're on the ground, you can find more mirrors. Right? No, think about it. Like, I can point enough mirrors at this until it melts. And if you make a stronger metal, then we can make it hotter, just add more mirrors. The only limitation to this heat potential is the engineering of the target. You understand what I mean by that? So we've gotten these things up to like 2,300 degrees, I believe. Like 1,900 is the operating temperature. That's really hot. 1,900? You can use this as a heat source to like melt steel. You can use this for like concrete plants. All of a sudden, it's cheaper to make heat this way than it is to burn coal. So now there's this industrial development where people are trying to figure out how to shift factories to the desert.
So it's cheap.
Super cheap, but it takes a lot of land. If you're driving on Highway 10, heading out to Nevada, right before you hit that fake Las Vegas, like at the border, you're like, oh, we're there. And then it's like, ah, crap, that was just the border. And then you got another hour to go to Vegas. Right when you hit that borderline, if you look to the left, you'll see 3 points of light. This is the new style of concentrated solar power. And this looks economically very feasible. For one reason. When you have electricity, nobody needs electricity. They still need coal-burning power plants because nighttime. Does that make sense? If you have solar panels, you're only making electricity when nobody's in your house. Daytime electricity usage is the lowest. So hooray, you just made something that nobody wanted. But when you get home at 5:45 and the sun is setting, that's when everybody turns on the lights and the TV and the air conditioner and opens the fridge and runs the microwave and turns on the computer and starts watching movies and playing video games. All the electricity is used at times when sunlight's not that available. But you know what? If you get this stuff hot enough, if it's really, really hot, you can put it in a giant underground thermos and store it. Like if it goes into the ground at 1900, it'll still be hot enough to boil water that night, and tomorrow night. They're saying 5 days of electricity after 1 day of good sunlight. Now you can make electricity almost the entire year with this. And if we figure out how to make a stronger tower, we can go hotter. We can go 7 days. If we can engineer a tower that doesn't melt until 10,000 degrees, then hooray, we can make electricity for 2 weeks out of that. Look at that. If you were doing research I would be like proud of you and everything, but still no cell phones. Yeah.
Is there like what's in the tower that can be transferred to the?
Dude, so that's a great question. Back in these days, they would use like oils, like motor oil, because you can get it 600, 700, 900 degrees, you know, like Valvoline. But now they use like rock salt slurry, like super saline solution, like 99% salt. Because you make all that salt gravel runny at like 1,000 degrees, and it'll go really far before it can evaporate. Like salt gas goes up to like 2,006, I don't know, some huge temperatures. So now the coolant isn't the limit, it's just the metal that holds it. I got a feeling that your children's grid will have a bunch more of these. Like, I think we're doing our last large-scale solar farms and our last large-scale wind farms, because I think this might win. Yeah?
What kind of metal do they use?
I don't know, I'm done. Shiny kind. Already there's a big movement to make these for industrial purposes. Because once you build it, you never have to buy more energy. Instead of coal every day, it's like, okay, hot forever. Yeah?
Wait, so I'm kind of confused about like the old style, and like does that store energy too, or does that?
Yep.
Okay. And what's the main difference between the two?
These, because of the economics and the scale, don't really reach high enough temperatures. I mean, think about this geometry. Look at my hands for a minute. When you're running a parabolic mirror with a pipe, at any given point, a slice of the pipe is only getting sunlight from a slice of the mirror. So the best you can do is two-dimensional sunlight focusing, right? But if that's a spherical set of mirrors, then you can go three-dimensional sunlight focusing. And so you could either build a huge three-dimensional parabola, or you can just take a field of mirrors and switch the angles so that they all accomplish the parabolic focus.
I see.
So now you can just expand eternally to get more sunlight at one point. There's no more temperature limit.
So it just has to do with the placement of the mirror.
Geometry, yeah. People are doing these like for, like heating all sorts of stuff. All right. Are we done with solar? Because now I got to speed up. Done with solar? Things go really fast. Are you sure? Okay. Number 31, hydroelectric is a dam that blocks a river from going downhill. How many of you have seen Bradbury Dam that creates the Lake Kachuma Reservoir in the Santianes River Basin? Anybody seen it from above, like from Knapp's Castle, where you drop in to ride? So if you know Knapp's and that view, it's a really clean visual. There's this huge canyon that in the valley gets blocked by this little tiny slice, and so it just floods with water when it rains. The nice thing about this is that you can hold a ton of water and let it out through a really small hole. Water's really heavy. Water pressure transmits perfectly. So if you've got like 100 square miles of water, 1,000 feet deep, and you let it out through a little tiny hole, all that pressure is focused on that one little spot. So you can shoot holes in a school bus, or you can spin really big turbines. The energy potential is really high. Hoover Dam makes unbelievable crap tons of electricity. I can't remember the number. But it's so much surface area, so much water coming out through just 9 of these little holes, that each of those is just like, just making like tons of electricity. Big old magnets, lots of wire. Yeah. Oh God.
Potentially, could you do that, but like with natural flowing water, like a waterfall, but it's less focused?
Yeah, you could. And so, historically, the very first water-powered stuff was all just places where water dropped. And you can just use surface motion of water. But the point of this is you can control it and you can store it. If you stop the water, then a little bit of flow piles up all the time you're not using it, so when you need electricity, you can let it all out at once.
But it's just more disruptive to the environment.
True. So the good news is, it's storable, the economics are obvious, you can get electricity whenever you want it, on demand, and that's important for alternatives. The bad news is, and this is the end of this whole entire conversation, turns out we like our rivers. And dams really ruckus rivers. Like the sediment has to flow, the wildlife has to travel, the river needs to have seasons. Because all those ecosystems are adapted to natural rivers and we tweak them with this. A dam is the exact opposite of what the river wants to do because water don't go down. Anybody want to talk more about dams? You'll notice I'm going out of order. I skipped hydrogen fuel cell. That was dams. Now let's go talk about wind, because wind is kind of simple. You just put the turbine in the air. Like explaining this on the AP test is just turbine generator and the wind, huh? There's an interesting change happening in wind power. I can give you a glimpse of the future. Raise your hand if you've ever been to Palm Springs, driving down Highway 1 near Indian Wells, heading down like Idlewild or... So, in that wind farm, you see a bunch of these small-scale turbines. If I'm not mistaken, there's like 500. And every one of those is disconnected. They're not worth servicing anymore. Those were 1970s technology that we gave up on. Their life cycle has ended.
So they're just kind of sitting
They've been
there.
replaced by medium-sized ones, like 40 or 50, that have also been replaced by like 15 large ones. And those are about to be replaced by 2 big-ass turbines. There's a simple trick of math. Anybody know the area of a circle?
Pi r squared.
Pi r squared. So radius gets multiplied. Radius gets multiplied by a whole integer, by 3 point something, after it is squared. In other words, if you make a little more radius, now you've got a bigger number and you're going to square it and you're going to multiply it. So a little bit of radius doubles your area. And people figured out, instead of building 2 of these, why don't I just make this one 10% bigger? And like now, instead of building 2 of those, why don't I just make it a little bit bigger? And the math is obvious and people are like, what is the limit of size? Nobody answered that. That is literally the current engineering crux, and PS, the biggest turbine ever was designed by a little company on Hollister in Goleta that designed this thing, which is enough to power like half of Paris.
And that's the city of light.
Yeah.
Is there a reason why they only have 3 wings, if not more?
Yes, it's yeah.
So, if the whole thing is like they creates electricity by spinning
Yeah.
a magnet and wires. If it's so big, like, won't that make it go like slower than if you had a bunch of fast small ones?
Yeah, so gears. Like transmission, like a car. So if you understand the gearing ratio, like even gears on a bicycle, you know, big ring, little ring on the chain. And so these are all, they all have transmissions, they all have electric kickstart, so they get it spinning, and then they start going through the transmission to get to the gears where it gets the most output at a maintained speed. There's been this amazing development where back in 1985, the capacity was like 1/3 of 1% today's capacity per turbine. And as it turns out, you can only make stuff so big because of the density of air, because of like torsional forces and shear strength. People figured out like we really can't get too much bigger around here. But then some nerds were like, there's a whole lot of wind and thinner air in the jet stream. How about a flying wind farm? Like that.
Is that like a real factor?
Yes.
It's a real computer generated photo. Some like grad student was like, hello, Mr. Gates, I have a proposition. Can I have 20 minutes of your time? And Mr. Gates was like, okay, $4.5 billion of funding. Not quite that simple, but there's basically a room full of nerds trying to figure out how to solve some little problems. Like, how could we protect square miles of airspace? How could we design robots that can automatically land something that weighs 30,000 tons or whatever on dedicated airstrips that are like half the length of Montana? How can we make an impossibly strong chain to hold this thing back and an impossibly giant plug in the earth? But it's worth solving those problems because 2 of these can provide the net sum of America's electricity forever. Because the wind in the jet stream is like 200 miles an hour 24/7. And air density up there is like less than 1/3, I believe, of what it is here. So the efficiencies are massive. And so there's a lot of different designs. People are like, we could try it like this or we could try it like that. And that's what this was, you know, like there have been these contests to design different ones. You all know Nick Riney? His brother is at some fancy school of doing engineering and he had a design on his phone. So I was lecturing and Nick Riney like texted his bro and his bro sent him back images of another one that was designed by Nick Riney's brother. Like this is like happening now.
Thank you.
Jetstream is just really burly. The problem is if one of these hits the ground, it's like 400 Hiroshimas of force. Like we gotta be really careful with that.
What is those?
How big are they?
They're big, bro. Like really, really big. Imagine like half-mile B-2 bomber boomerang shape with like 6 turbines that are like 1 scale higher than the largest we use on Earth now.
Big.
Big.
Is there like a wire that goes back to Earth?
Yes.
Transmitting the electricity?
Yes. Yes. Yes.
Can't we just make like a really long stick with like
30,000-foot jet stream. So what we could do is maybe a very tall elevator to outer space. It's called a space elevator, which is a tethered synchronous orbit satellite. It's an actual thing. Like while you're all sitting here thinking that you're at the end of science, all the smart people are like, let's keep going. We're all gonna die either way, no big deal. Next. I'm not done and we're running out of time and I'm freaking out.
It's okay.
You seem very stressed.
It is true, I should add, that wind turbines kill birds by the bazillions. I had to walk through the Tehachapi wind farm and it was like pillow fight status.
But if we put them in
Like
the
there were
dead stream-
feathers stuck to all the chain link fences and there were like piles of seagulls like this big sometimes where a whole flock just got shredded. Like, it's no joke. If you think about the evolutionary forces that have designed a bird, they don't look up. So all the birds do this and they see the turbine coming this way, no problem. But they're doing this and they don't see the turbine going that way, they just get snapped. And like, the bird losses from wind turbines are massive. And birds like to fly where there's strong winds, which is where we put. So it's like, oh, that's where the birds are? Gotta put the blender right there. It's for real. And so apparently some like grad student somewhere got a really fancy publication called Duct Tape and a Kazoo. Because on the cover of this magazine, he was like, with like duct tape and a kazoo on a wind turbine. Because he demonstrated that birds respond to noises, so now we're making noisier wind turbines. They make like vibrations that we can't hear, but they bother birds. And now the challenge is how to keep the bats alive. Because bats are smart, they're agile, they have sonar. So they definitely know the turbine is there. They never get hit by a turbine. You've all seen the agility of bats in flight, right? Their wing is evolved from all of these bones instead of these. So their wing has all this dexterity so they can just affect their flight spontaneously in major ways. So they fly right around the turbine, no problem. But because the turbines are shaped like a wing, there's less air pressure in the back of the turbine.
And it sucks them back in.
And it sucks the lung out of their bodies. And they deck like hemorrhaging out the face. And birds are nice and everything, but bats are really important for our economy because they regulate bug populations, which have to do with disease transmission in agriculture. So wind turbines are actually a really touchy subject. But I'm not done and we're almost out of time.
Hey, am I cutting through the circle? Or am I just around the base?
I don't need the circle at all. So do whatever you need. You can throw away the circles.
Yeah.
Anybody else? What?
How fast do they turn?
Pretty, like the tip is moving a lot faster because it's covering the same, more area at the same time. So the angular velocities, the tips are moving at like hundreds of miles an hour. Really fast. Okay, back to me. I gotta move on. Tidal power is the last thing we're gonna do today, and we'll come back to hydrogen fuel cells. There's 1, 2, 3, 4 types of tidal power, and 1, 2, 3 have already been rejected. 1, 2, 3 have extremely limited applicability, so they're not really catching on. I gotta get all the way to number 4 in 17 minutes, so please discipline your interruptions. Because I obviously cannot. Option number 1 is called tidal barrage. The writing is getting smudged because dumbasses were putting up Post-its yesterday. So I've also typed it up there. Tidal barrage. And the idea is you bar the tide. Like you take a bay and you block it with a dam. It's a bay with a dam. Bay, dam, ocean. And you know, you can open and close the dam. You can control that. So watch this. At low tide, you shut the dam. You wait for the ocean tide to rise, and then you open it so that all the ocean fills up the bay at once. Right? And the tide's always rising or dropping. So you can get that math right so that the water's always flowing into the bay, or you wait for low tide and the water's flowing out of the bay.
This way doesn't work.
Good things and bad things. Good thing, you can schedule this. I know high tide in 75 years down to the second. You can do the math, tidal variation, volume of the bay, total electricity. I can tell you that on August 24 of the year 2075, we'll have 300 kilowatt hours at noon. You can schedule it. And that's the only one of all these that you can schedule with certainty. That's important. But it only works at extreme latitudes, like far north and far south. I don't know if you guys realize this, but there's no high tide at the equator. The really strong tides are at the poles, and that's not where the humans are. The humans are all pretty close to the equator. We're all between 30 north and 30 south. And so there's just not a lot of tides where the humans are. All the tides are like in Nova Scotia and like Tierra del Fuego and stuff, and like who needs electricity out there? These are also expensive to build and maintain in really fragile ecosystems. So this is kind of a dead end for engineering. Here's another image of the same thing, and basically we're over it. Number 2, where else can we use water's inherent movement? We could use currents, or we could use wave action, tidal surge forces. To get a current, you just need like a wind turbine for water. Like this. So that a place that always has current, like Point Conception, North Shore, you find a place that always has current, and then you just put a turbine right there.
Doesn't it like kill fish? It's like the current is there.
You have to gear them right so that they're not going too fast. One of the big problems is water always finds the path of least resistance. So when you add magnets pushing past a wire resistance, the water just goes around. And so like the hydrodynamics of this are barely operational. And you still have complicated machinery in the ocean, which will screw any machinery. Everybody who's had anything to do with the ocean will tell you that the ocean is extremely hostile to engineering. Submerged turbines operate on current, barely functional, saltwater sucks. And tidal reefs, that is a lot of force. You've probably been standing on a steep sandy shore and kind of been made to tumble by water moving up and down the sand.
Does that say reef?
Yes, tidal reef, like this.
Gotcha. Oh, I wrote reef.
And there are a bazillion ways to run these. But there is a problem. Every place with shallow water is ecologically sensitive and expensive. Like, where's a beach that you can buy waterfront for very low prices? Every place on the planet,
Antarctica.
every place on the planet, the shore is expensive and ecologically sensitive. So this is probably putting it in the wrong place. So that's kind of out. Option number 3, what if instead of using the water's movement, we use the water's temperature? There's parts of the ocean that are really hot. And get this, what if there was a coolant with a low enough boiling point that you could make it into steam on the ocean surface? this is a big deal. It's kind of a theoretical solution. It's only been tried once that I'm aware of.
Did it work?
You need coolant with a low boiling point. That's right there, and you gotta remember this because that's the fly in the ointment here. But if you can get something that evaporates at 85 degrees, all you gotta do is find ocean water that's 86 degrees, right? You put the coolant in a pipe, take the heat of the ocean to make that coolant evaporate, and then that expansion will power a turbine. So you can have these things offshore, where we really don't care if it's out in the water a bit. And then if it's offshore, you can just send the electricity back to the town, and they do have one of these in Hawaii. And this probably would work in Indonesia if we could get 1 trillion gallons of ammonia.
They used ammonia?
I think so. I mean, it's some kind of an ammoniated substance.
And if there was a spill, that would be really bad.
But you know exactly, and like the chemistry of these coolants and the cost of these coolants and the fact that almost no place is hot enough is just too many problems. But there's one type of ocean power which makes really good sense to Jose.
Do you want these cut into like X's or T's?
Cut along all those pencil lines.
Just right now.
Yeah.
Those things.
So I need this piece and this piece and this piece and these pieces. The straight lines aren't too important. The curved line is a mold for something permanent.
Okay.
The straight lines aren't too important. I'll probably end up cutting those straight lines again. I'm shaving some stuff off of them. Okay, for the purpose of this explanation, I need to rely on something that you've all experienced playing with a cup in the bath. So, try to focus, but let's pretend I'm in a bath right now.
Yes, sir.
I'd like everybody to imagine that this is the level of the water. Let your mind run wild.
What do you say, man?
So you want to take off his shirt first?
And now,
I said for you to take off your shirt. You need more visual.
I take my cup, I get some water, I can go splash and I can laugh. I can scoop it up and I can blow bubbles with it. I can play with some hydrodynamics that you all understand. I can trap an air bubble and let it go and it'll pop up, right? I can fill it up with water and try to pull it out, and then when I let it go, that water's going to level itself again. You all understand these ones, right? I want to remind you, you've all had the relevant experiences, but the explanation can get tricky. Imagine I've made a hole in my cup. Now, when I push this into and out of the water, there's going to be a piston of water on the inside that's driving air in and out through that hole. Do we agree with that? Yeah? If you were standing right here, you would hear air leaving, and then you would hear air coming in. Agreed? This is all okay with everybody? I could go and move that air by moving the water. I can make constant wind, outgoing and incoming, if I can put a one-way switch on that valve. Right? Outgoing, incoming, outgoing, incoming. If you go to a place that has an ocean that moves, like all of the oceans, especially if there's wind swell, like a whole bunch of coastlines, then air is either getting pushed out or getting pulled in. It's called an oscillating water column, and you turn surface action into wind power. Casey, can you bring me that fan? Like unplug it and bring it over here? I'd like everybody to imagine this, because we got to do a lot of make-believe. This is, I don't have a lot of photos to show you. Thanks, homie.
Would you like an exact in there? I'd make this a little bigger.
Look in there, yeah, maybe. Watch this. No. Watch this. When the swell goes up, air gets pushed out. That would go on this side and spin the fan. And when the air gets sucked in, that would come this way and spin the fan again. If you have outgoing air and incoming air, that blade is always spinning. Does that make sense? Like wherever the water drops, that's sucking in air. That can be a separate pipe, then the water rises pushing out air, so you go like this on your turbine. And you can bank these. You can put a whole bunch of these along a pier, for example. So you'll have like 10 of them pushing up and 10 of them pushing down. So that turbine can get cranking. Just surface movement of water can get you like a spinning turbine that goes 24/7. You can put these on a coastline. You can make these extra large in places where surge magnifies, like in a bay. Or, my favorite, you can put these out at sea, like a barge. It's just barely above sea level. Here's a crazy thought. These add habitat. Because they make like sheltered places where stuff can hide. You can hang a bag of oysters and now it's an aquaculture farm. Every place you've got a pier, you can just stack like 20 of these on the bottom and get like the electricity for the pier. Or you can just get barges and put a bazillion of these out to sea. Just connected by big extension cords back to land. Almost all humans live on the coastline. 1/3 of humanity lives within 300 feet of sea level elevation.
Yeah.
So you can make tons of electricity any place that has wind action, because the oscillating water column translates surface action into wind power.
Is that what OWC stands for?
Oscillating water column. We did not get to the hydrogen fuel cell, and we'll do geothermal as well on Friday. I'll answer all your questions about these. Made it! I didn't charge anyone. I can tell you how many times you paid if you want.
No, because I Venmoed you, but I also paid you cash. Remember, I got you.
I don't remember, but I remember getting cash. I remember getting Venmo, and I trust you if you paid cash.
I did.
So do you want a refund or do you want more cookies?
I'm just gonna get one cookie.
Haha, sucker!
Like, I don't care. I don't know.
Did you stop streaming?
What?